Yeah, this kind of organizes everything that we're doing. Well, to wrap up our short week here, what we're going to do is just solve some problems involving right triangles today. There's really no new information. We're just going to use the trigonometry that we've now established to work out a few examples. There's only really one thing on the agenda, and that's this. There's 6 problems I've got for you for samples, but we just want to use the trig ratios. We're just going to use sine, cosine, and tangent. When you're working with triangles, those are the only 3 you really need. The other 3 have purposes outside of working with right triangles, so we'll just use sine, cosine, and tangent today. And we just want to solve some applied problems. So we're going to jump right in. Here we go. These to some degree progress from the ones that require the least amount of work to the ones that require the most amount of work. So these the first few should be a little bit more clear. The later ones out of the 6 that we're going to do will probably take a little bit more thinking. But let's take a look. First one, we're going to stand 125 feet from the base of a building, and we want to figure out how tall it is. Now, we are assuming that this person who is looking at the building, their eyeballs, where they're looking, is not right at ground level. And just to keep the problem fairly simple, we're going to assume that the person is a little bit taller than 6 feet and their eyes are exactly 6 feet above the ground to keep this nice and simple. So what we end up with is a triangle. If they look straight ahead, they're going to be looking at a line parallel to the ground and 6 feet above it. And if the viewer looks up to the top of a building, and what a transit does is it allows you to look at different things, and it measures your angle as you change your direction that you're looking. So we know that this angle of incline is 27.3 degrees. Angle of incline or angle of inclination is an angle up from horizontal. Some of your problems in the homework today will deal with an angle of depression or angle of decline, which is down below horizontal. Now we know that we're 125 feet from the building, so we want to find the height of the building. Well, first of all, we know how far it is from here to here. That's 6 feet. So we need to figure out how far it is from there to there. We'll call it x. So what trig ratio are you going to have to use here to solve for x? You want to find the opposite, and you know the adjacent, so you're working with tangent. The 2 that are of interest are opposite and adjacent. So what's that? Yeah, we're assuming that the building is straight up. And so we're going to assume that it's perpendicular to the ground and therefore perpendicular to our line of sight. So we can say that the tangent of 27.3 degrees is equal to the value x over the adjacent side of 125 feet. So to solve for x, we're just going to multiply both sides by 125, and x equals 'Whoops. Tangent of 27.3 times 125. And if you crunch that out, you're going to end up with a value of x of 64.5. No, that's not the height of the building. That's how far it is above from our line of sight directly across. And so what is the height of the building? Add 6 feet to that. .5 feet tall. We're done. We've got a roof truss here. We want to figure out based on the information that's given there, we want to find out what the length of the segment DE is, and we want to find the angle measure for DEF. This one takes a little bit more thought. I'm going to give you just a minute. You've got the problem in front of you. Take just a minute, see if you can see how to figure those two out. This one is not just a one-step problem like the previous one was. The whole right side of that truss is useless. We'll just work on the left side. Thoughts or suggestions? Anybody have the insight into how to figure out what the value of DE has to be? Well, here's this. You're gonna dig this, because one little line is going to make the problem absolutely apparent. Okay? Add a line. Add an imaginary line, right? Here. Now I'll stand back while you all sigh. Now you've got two right triangles. Okay? And both of them are useful. You know, you've got this one here on the left, and you've got that one there on the right. Now, can you find the height of that? Sure you can. Yeah, let's go and find the length of that little imaginary line that I just inserted. Let's call this x. Okay? So let's find x. Now, look at the 87. Don't be misled. Is the 87 any good for finding the length of x? It's not, because that 87 does not apply specifically to this triangle. So what we do have to use, we want to find the opposite. We know the hypotenuse. We have to use sine. So we know that the sine of 28.0 degrees is equal to the opposite, which is x, over 63.0, the hypotenuse. Which means x equals, I'm going to drop a sig digs here just to save a little bit of space. 63 times sine of 28 degrees, and x is equal to 29.58. Yep. So we know that that is 29.58. We'll leave that just as x to save a little space. Okay. Well, that's a start. Let's call this point down here G so that we've got a little label for it. Now we can find FG, right? Would you agree with that? We can find FG. We could do it by Pythagorean theorem. 63 squared minus x squared is FG squared. True. Or we can use trigonometry. What trig function would we use to find FG? Let's call this segment right here, let's call it Z. Let's call this segment Z. Let's use trig to do it, just because it's fun. I know you can all do Pythagorean theorem. Let's practice using the trig. So what function are we going to use to find a Z now? We could use tangent, but that would rely on the fact that we'd be using x. Let's stick to using information that's given. So instead, let's use 63. So we know the hypotenuse. We want to find the adjacent. Let's use cosine. Very similar to the one that we just found. We know that the cosine of 28 degrees is equal to adjacent, which is z, over hypotenuse 63.0. And so z equals 63 times the cosine of 28. We just found z. It's equal to 55.63. Yeah? Okay, well now we found a z. That's, it's interesting, but that doesn't get us angle E or DE, which is ultimately what we want. But now what can we do with z? Subtract. We can find y, this section right down here. We can find that by subtraction. So let's go down here. Y equals 87 minus 55.63. And that little segment down there turns out to be 31.37. Now we're cooking. I'm going to clean up this picture a little bit now with the information we know. We know that this segment right there is 31.37. Okay, well, now let's find DE. DE, just use Pythagorean theorem. Let's call this DE, let's just call it W. So we know that W squared is equal to 29.58. Let's go down here. And we won't go through all that algebra. You're skilled at that by now. W turns out to be 43.1 inches. Okay, we're half done. We found the answer to the first question, 43.1 inches. And finally, we need to find angle DEF. Let's call it, let's give it a name. It's a little bit easier here. Let's call that angle theta. Now, what trig function do you want to use? You could use any of them, but the best one to use, let's use tangent. In case we found something wrong in this 43.1, let's use tangent. And so we know that the tangent of theta is equal to the opposite, which is 29.58. The units will cancel, 31.37. So theta is the inverse tangent stop there for a minute. This is the first time today we've had to work backwards to find an angle, but we got our opposite. We divided it by the adjacent. And you end up with 43.3 degrees. We're done. We found our segment, we found the angle. A bolt circle. A little background information. A bolt circle is just, if you've got, well, a good example of this is when you bolt a wheel on your car. Okay, the lug nuts are in a bolt circle. They're a pattern of bolts that are all falling, so the center of the bolts are all on a circle. It'll look something like this. We've got a bolt circle with 5 bolts. So that means that we're going to have 5 bolts that are all falling so that their centers are in a circle. 5 of them is going to look something like this. There'd be a 5-bolt bolt circle. Now, this tells us that our bolt circle has a radius of 5.25 inches, 5 1/4 inches. So from the center of the bolt circle out to a middle of the bolt, it's 5.25 inches. Bolt circles are usually given according to the circle diameter or the circle radius, naturally. We want to know how far it is between the centers of 2 adjacent holes. Well, we don't even have any triangles there, much less a right triangle. So where do you want to draw your triangle? Let's go to an adjacent center, right there. Well, there's 2 sides, and let's complete our triangle with that. Now, what we want to find is this distance, D. That's what we want to know, how far it is between the centers of 2 adjacent circles. But is that a right triangle? Certainly not. We can split it up into 2 triangles, and they'll both be right triangles. So we can just break that right down the middle. And now we've got two right triangles, so let's just work with one of those. So that's all well and good. We could find D if we just knew what this short side of this triangle was. Let's call that x. All right? If we can find x, we'll double it. We'll have the answer to the question. Well, that's all fine, except for we don't know too much else. But you do know a little bit about this triangle. What else do you know about that triangle? We know that the whole circle is composed of 360 degrees. So, which means how many degrees is it between any two adjacent circles? So, for example, from there to there, how many degrees will there be in here? 70 what? 72. How? 360 divided by 5. So, between any two adjacent holes, it's 72 degrees. Which means it was 72 degrees between these two holes, or in other words, how many degrees are there in that acute angle? Half of that, 36 degrees. So we know that triangle is 36 degrees. Well, now we're set. Because we can use this triangle, and we now know we want to find the opposite. We know the hypotenuse. We're working with sine. We know that the sine of 36 degrees is equal to x over 5.25. Scooting that down here. That means x is equal to 5.25 times the sine of 36 degrees. Which will tell you x, or half the distance between two adjacent holes. That works out to 3.086 inches. That's good. And then our distance, which is 2 times x, is 2 times 3.086, or in other words, yeah, we were given 2 decimals on our bolt circle. We'll keep that a theme. 6.17 inches is our distance. And that one's solved. So it's 6.17 inches between adjacent holes. This is my personal favorite of the day. It's not the toughest one, but it's the best. It's the coolest. Definitely going to need your little handout with this diagram on it. We want to find out what the dimension y is. We've got a piece of stock there, given a few dimensions, but there's a V cut into that with a 66.40 degree angle down at the bottom of that V. There's a bearing, a ball bearing sitting in there with a diameter of 37.0 millimeters, and we want to know how far above the surface of the stock that bearing will sit. That's the dimension y. I'll give you a minute to look at this, kind of like the truss problem. See if you can spot how to set up some triangles that are going to tell us that. Well, anybody see anything? How can we get there? You want to split it in half. Yeah, we can disregard. It's a symmetric shape, so we can disregard half the picture. You want to draw a line straight up here? Okay, I like that idea. Okay, we're going to draw a line right up the middle. We're going to do that. Here's our general approach. We need to figure out two distances. Our reference point is going to be right here. Okay? We're going to figure out two things. One, we're going to figure out, in order to find the distance y, there's no way we're going to be able to set up a triangle up here so that y is some side of a nice triangle. What we'll do is figure out what the distance is from the bottom of the groove up to the top of the ball. And we'll figure out what the distance is from the bottom of the groove up to the top of the stock. And we'll subtract the two to find out how far above the stock the ball sits. Does that make sense? So we're going to figure out the distance from here up to the top of the surface, and from here up to the top of the ball, we'll subtract our two results. So let's start out with, we could do either one first, but let's start out by figuring out how far it is from here up to the top of the stock. So I'm just going to extend this all the way across. And we want to figure out this distance right here. Let's call this distance well, I was going to say D for depth, but that's probably confusing with diameter. So let's call this H. Let's call that H. Now, how can you find out what H is? We've got a right triangle in here. Yep. Right here, we've got a right triangle. None of the dimensions of the ball are relevant towards figuring out the dimension H. All we care about is that notch that's cut in the rectangle. So we know that the entire V is 66.4 degrees, which means this angle down there is half that, 33.20 degrees. Now, in order to solve any part of that triangle, we need to know at least one side length. What's the one side length that we do know? The top is 25 millimeters. 48 from the center to the edge, 23 flat on the top, which leaves 25. .25 millimeters up there, so we can go ahead and find H. Yep, we're dealing with opposite and adjacent. So the tangent, 33.20 degrees, equals the opposite of 25. I'm going to drop the sig digs to save space over H. Solve that, and H is equal to 25 over, here's a case where we can do our switcheroo there, over tangent of 33.20 degrees. And that's going to give us a height of 52.99. Is that right? No, never mind. 38.20. How's that? Sorry, read the wrong one on my paper. 33.20. Sorry, 38.20. Thank you. Those are millimeters. 38.20 there. Okay, now let's turn our attention over to the ball. Everybody got that? I'm going to get rid of that, and now we'll work on the ball. Let's clear up some room here, okay? How are we going to find out that overall height? Now we're going to draw. We know what the distance, or this radius is. This goes back to one of the properties of circles that we worked with earlier. If you take a radius and it extends down to a point of tangency where a tangent line contacts the circle, what do you know has to be true about these two lines? They have to be perpendicular. Okay, so that's good. That gives us a right triangle. Now, we got to know something about that right triangle. Well, we know the angle. That's still 33.2 degrees. We don't know this distance. We don't know that distance, but we do know this distance. It is the radius of that circle. We're told that the circle had a diameter of 37.5, so if we divide that by 2, we get 18.75 millimeters. Okay, well now we can find this value. Let's call the hypotenuse of that y. We haven't used y yet, so we'll call that y. Now we know opposite. We want to find hypotenuse. Sine of 33.20 degrees equals 18.75 over y, which means y 34.24. Okay. That's just from the bottom up to there. We now know that that is 34.24. Let's mark that in here. Okay, well, we do know the rest of that distance, though. It's another radius, 18.75. So to answer the question, which we can now do, y is going to be equal to, oh gosh, I shouldn't have used y back there. See the problem? Y was a pretty bad choice. Y was up here. We were trying to find that. How's that? We didn't use x anywhere, did we? Okay? Got that? All right. So now we're set. Y is equal to, we know what the total distance is. That's going to be 34.24 plus 18.75 minus 38.20. And if you subtract that, you end up with the distance y. And anybody have that? 14 point something? 14.79 is what I have. 14.79 millimeters. There it is. We're done. We found it. Ship leaves port. Couldn't have a bunch of trigonometry word problems without a ship leaving port or an airplane flying some direction. Okay, well, our homemade ship leaves port and travels 81.5 miles on a heading of north 42 degrees east. Now, your textbook has a lot of these type of problems. A little about the headings. First of all, it says that we're going north, but our heading is 42 degrees towards the east. So north 42 degrees east means you start out north and then shift 42 degrees towards the east. So that means our heading is approximately that, where this angle here would be 42.0 degrees. And we travel 81.5 miles. Okay, that's the first part of the trip. Then it turns and heads 37.5 miles due east. And it travels 37.5. 37.5 miles due east. And the question is, how far from the port is the ship? So we want to find that distance. Well, next week we're going to start working with oblique triangles. What we've got is a non-right triangle there. There's a law that we could use to find that pretty easily, but we don't have it yet. We only have right triangles. Okay. So, how do you want to find this distance? Again, any insights? There you go. Let's extend this back. Now we've got a right triangle. Now, as long as you put that triangle in there, it's not too much trouble, because we can use Pythagorean theorem to find this side if we know this side and this side. The question is, can we find this side and that side? Sure we can, because we know that this triangle is 42 degrees and we know the hypotenuse. So let's call this distance right here, let's see, x. Is that a safe choice? I think it is. Let's call that x. And we can find x. We know that the sine of 42 is equal to x over 81.5. With that in mind, x will be 81.5 times the sine of 42. I'll save that space and note that x works out to be 54.53 miles. Okay, everybody agree with that? X is 54.53. Okay, we can fill that in the picture then. All right, well, we also need to know how far north it went. So let's find y. Again, same basic principle, but now we're going to have to use cosine. Cosine of you could. Yep, cosine of 42 degrees is equal to y over 81.5, and if you do that, y will be equal to 60 point what? I had 5.6. Perhaps I rounded wrong. 5.7. Well, now we're